Good afternoon, everybody, and welcome to the Dayton Hamvention Antenna Forum. And happy Friday afternoon. I know it's a little warm in here. We're doing our best to get you cooled down. You can find previous Antenna Forum publications, the slide decks for about the last 20 years at k3lr.com. Just click on Dayton presentations. And I'm always looking for future presentations. Just send me an email, k3lr@k3lr.com, and I would love to hear what you'd like to see next year. We have 4 great presentations today. They are each about 45 minutes in length, and the presentations are from W5ZN, K2TR, W8WWV, and WX6SWW. And so I think you're going to find it to be an entertaining and enriching 3 hours. Our first talk today is comparison of vertical arrays for low band receiving. Please welcome Joel Harrison, W5ZN.
Thank you very much, Tim. Good afternoon to everyone, and thanks for being here this afternoon. As Tim said, I'm going to be speaking about comparison of short vertical arrays for low band receiving. I have about 40 to 45 slides, so I'll be moving through those as efficiently as possible. Let me see if I can get there we go. So I would encourage you to go to my website and download, if you haven't already, a rather extensive paper I have on this topic that this presentation is based on. And what we want to try to cover today is just a little bit about low band propagation, because there's no way you can start comparing antennas until you understand propagation on the band that you're dealing with. I'm going to tell you a little bit about my experience with vertical arrays. Then we're going to talk about the differences in vertical arrays and an approach to comparing low band receive antennas. A little bit about what test equipment that I used and the calibration, then the data collection and the results. So geographical differences, it matters when you're comparing antennas. So if I'm sitting here trying to compare an antenna to someone that lives over 1,000 miles away on the East Coast to where I live in Arkansas, you're not going to have an accurate comparison. And even sometimes the exact same antenna is going to perform different in 2 locations. Frank, W3LPL, and I both have one of these vertical arrays that I'm talking about, and they're pretty much identical. And the geographical differences really, there's difference in the performance. So closer to home, within about 450-mile radius of where I live, I have 3 stations that I like to compare signals to. One of them is my good friend Dave, W0FLS up in Iowa. My other buddy Dave down in Texas, W5UN. And then Larry, K5RK, who's also down in South Texas. And the propagation differences that we see on 160 meters a lot of times is significant. Now, even closer to home where I live, I have 3 good friends of mine, K5UR, WD5R, and K5EJ. They're both about 20-25 miles from where I live. And sometimes when we're listening to signals on 160 meters, what we see in differences between signal to noise ratios and signal strength is just sometimes really eye-opening. So 160 meter propagation is really beyond the scope of what we're going to talk about today, but you need to understand it. So I want to encourage you to read all of the information that Carl, K9LA, and Frank, W3LPL, have published on propagation. There's a link here to Carl's website, which is in the presentation, and Frank's information is kind of like Santa Claus. It's out there everywhere, all right? So several years ago, when I really became serious about 160 meters, I started experimenting with beverages and loops, and these all worked well, but I sort of have this, I don't know, it's an obsessive addiction, I guess you would call it, that I want to be able to hear better. So back in about 2008, my good friend Bob McGuire, N4HY, told me about this vertical array that he had done a lot of extensive research on and was interested in putting it on the air. So I said, hey, I'm going to build one. So I did. And its performance really exceeded what I had seen on beverages and loops. And then after I had this array out for a couple of years, Lee K7TJR with high Z antennas was producing this high Z-8 array. And a few people had those and really had some good results. So I was like, gotta get one, gotta try it, gotta have it. So I did, and I installed it and was very pleased with those results. We're not too long after that. John W1FZ came out with this 9 vertical array. And of course, again, having an obsessive addiction, I'm like, I gotta have one, gotta get it. So I actually wound up with 3 of these vertical arrays that I was trying. Now, there's differences in these vertical arrays, and it's very, very important that they be understood. And here's a good example. A few years ago at the top band dinner in Dayton, I'm seated at a table, and a ham said, hey, I'm putting up one of these 8 circle arrays. And I said, great, which one? And he said, the one with 9 verticals. So I'm like, something's wrong with that math. So we're going to discuss today what are the 3 most popular vertical arrays that are put in a circle so that you can achieve 8 received directions from those. So the first one we're going to talk about is referred to as a Broadside End-Fire Array, or a BSEF array. Now it uses 8 verticals in a 350-foot diameter circle. That's pretty large. But for any one direction, you are only using 4 of those verticals, simply because it is a pair of end-fire verticals. So as you switch around to the 8 directions, you're switching which set of 4 that you're using. Now this is a low impedance system. The input to each of those verticals is 75 ohms. There's no amplifier or anything else that's really required at the base of the vertical, with the exception of a little matching to match the vertical to 75 ohms. Now, you get a very good pattern with this. You have a 3 dB beam width of about 58 degrees, and it has a front to back from the modeling data of about, about 25 dB. This is the easy neck pattern here. So then the high Z array that I talked about that K7TJR designed is an 8 vertical array in a circle. It's a 200-foot diameter circle for 160 meters. And the difference in this design is, number one, it's a high impedance system, so it actually has a little high impedance amplifier at the base of each of the vertical elements. But it uses all 8 elements. Regardless of the direction that you're interested in, all 8 elements are active. They're just phased differently, as shown here on the left. This has a very, very excellent pattern. It has the same about 58 degree 3 dB beam width, but has a very excellent front to back of about 25 to 30 dB. So then we have the YCCC9, the one that John designed. And again, this uses 9 verticals, but there are 8 verticals in a circle. The circle diameter is about 120 feet. But then you have 1 vertical that is in the center. And the reason is, for any one direction, you're using 3 of the verticals in one specific direction. All right? So as you switch around, the center vertical is always active, and then you're just selecting which of the other 2 as you go around the azimuth that you're using. This has a much broader beam width, about 75 degrees for the 3D beam width, which is understood, right? Because it's an end-fire array, basically. It's not a broadside array. But it has about, because there's 3 verticals in line, you can get some really impressive front-to-back rejection from this, sometimes 25 to 30 dB. All right, so we have to talk a little bit about the beverage antenna. Now, everyone has heard of the beverage antenna. It's been around forever. It was introduced back in about 1921, and it rightfully has become the standard that we compare all low-band antenna receive antennas to. There have been a lot of books that have been published on it. Vic Misick published the Beverage Antenna Handbook several years ago, back in about 1977. Unfortunately, and that had a lot of really great information in it. It was the first real publication that had some good information for radio amateurs. But that's no longer in publication, but a lot of the information that was contained in the beverage handbook has been captured in low band DXing and has been expanded upon. So that has now, low band DXing by John DeVolder has become the really go-to source for beverage antenna work. But there's another reference that is very, very important to note here. And it's some work by Greg Orty, W8WWV, and Greg's sitting right over here, and he's going to be presenting here a little bit later. Greg has done an extensive amount of work on beverages in recording simulation and modeling and simulation data, and some on-the-air performance for beverages of different lengths, different designs, different heights. And I have the link here on the screen for his website. But one of the things that I really, really like about Greg's work is he has quite a profound statement that says, for me, the beverage represents a yardstick which can be used to compare the performance of other receive antennas. That is so very true. And actually, in my work that I have performed in every comparison that I make, I have 580-foot beverages that I use, single wire beverages, and I include those in all of my comparative results. All right, so this is my test range that I have in Arkansas. Now, I'm very fortunate that I have 30 acres, so I've got a lot of room that I can use to put antennas out in various locations. All right, you can see up in the upper right part of the screen, you know, I have the YCCC 9 antenna that's located about 500 feet northeast of the shack. The high Z8 is setting out there to the right. It's about 850 feet out to the center of that array. And then the Broadside End-Fire Array is south, and it's about 800 feet or so south of the shack. Now, I try to keep these separated from my transmit antenna. I have a big gain transmit antenna. It's a 5-element parasitic array that K3LR has popularized, and it's setting over there on the far left of the screen is where that sets. Then I have the 4 beverages that are laid out northeast, southeast, west, and northwest that you can see on the screen. So this is how I lay everything out, where they are, and how I arrange things for my test. So the parameters that I have used for my comparison is the first thing I did was I compared modeling and simulation results. And then I collected empirical data because I wanted real on-the-air data to see how that compares to the modeling and simulation. And then documented any differences that we might see from that data. And then actually analyze that and say, well, really on day-to-day operation, is there anything that I can really tell a difference in these? So here's the test equipment that I used for these tests. I had 2 K3 transceivers. I had 2 LP PAN software IQ PAN adapters and 2 NAP3 PAN adapter displays running on 2 separate computers. This allowed me to look at 2 separate antennas at exactly the same time and record the signal data. Now, also in order to do this, I have a K9AY RAS8 antenna switch, and this has 2 outputs on it, and it allows me to use 2 receivers at the same time, and I can switch real quick between those 2, or actually put 2 antennas, on each radio at the same time. You have to calibrate this test equipment as well. You can't just throw things out there and assume everything is working all right. What I use for calibration, and you need one of these. I don't have any commercial connection with Elecraft, but if you don't have a Elecraft XG3 signal source, you need to buy one because they're invaluable. All right. So you want to calibrate the equipment to make sure any known variable is removed from the system, or at least that you document it. All right. And so prior to the start of each of the measurements, I would inject a minus 73 dBm signal, all right, into the cable, my signal cable at the far end where the receive antenna was, and to verify the loss in the cable and my calibration that I have in the system. So these arrays, you get out to the center of the array and it's about 800 feet out there. I'm using RG11 for my signal cable. That's 75 ohm cable. That's the impedance that I'm using for my receive antennas. RG11, I'm sure everyone's familiar with it. That's really the 75 ohm version of RG8, all right? So on 1.825 megahertz, through that 800 feet of cable, I measure 2 dB of loss. That's fine, that's very acceptable, and I verify that daily. So when I come into the shack, prior to the radios, I have those 2 outputs on the RAS8, right? So that's going to give me some other attenuation. I have 2.5 dB of loss that I've measured there. So when I actually get to the radio, to the pen adapter, my minus 73 dBm signal that was injected far out at the antenna is actually shows 4 dB of loss. How about 4.5? It's minus 77.5 dB on the pen adapter screen. And I verify this anytime before I start taking measurements, all right? And then starting to proceed. So there's a number of things that you need to record when you're doing signal comparisons, okay? And you need to document this data in 8 directions or however many directions maybe you want to compare your antennas in. I'm comparing in 8 directions. I'm going to record the noise floor level in each of the 8 directions. I'm going to record the forward peak of the signal. I'm going to record front to back data and front to side data. Now, for these measurements, all right, you don't even think about doing this with an S meter on your radio. You're not going to get accurate results, all right? So I was able to use these pen adapter displays that I have. I could calibrate those in 1 dB to 1 dB resolution, all right? And I could really measure some accurate results. All of my measurements were recorded in CW mode with a 400 hertz bandwidth. So I recorded data on 160 meters over a 10-year period with all of these arrays. And I recorded about 100 DX stations to collect this data. Now, a few of these 100 stations were the same, but they were the signal information that I recorded was from a different part of the day, a different part of the solar cycle, or a different time of the year. So I felt like that was a good comparison to make over time. And also, a lot of these DX stations that I was recording were really too weak to be able to acquire any meaningful front-to-back ratio, or front-to-back rejection or front-to-side rejection. So in order to collect data for that, I used about 30 stations in the United States to do that. Now, that's doing so with the understanding that I'm going to have, different arrival angles or different conditions from stations that are local within the country. But regardless, the results from those stations are very accurate. So when you start recording your noise floor for each array, you have to take into consideration whether it's an active or a passive system. And any preamplifiers that you place in the system will affect the noise floor of the array. And so I did this in each of the 8 directions for each of the arrays. Quite often, really nearly daily, I would record the noise floor and make sure nothing had changed. If something had changed, I obviously need to track it down and see what's going on. So for the 2 8 vertical arrays, the high Z and the BSEF, the noise floor in the shack through my long cable and through the switch averaged around a minus 120 dBm. That's pretty good. That gives me sufficient gain from the array and gives me a good baseline to record signals. All right. Now, the output of the YCCC9 is low, so I do have a preamp on the output of it, which is recommended in the design. But for that, through its 500 feet of feed line, I have a minus 125 dBm noise floor. Now, of course, that's 5 dB less than the other arrays, but I'm recording signals based on the noise floor, and this is very adequate for comparative measurements. The 4 beverages that I have a very good signal from those in noise floor without any amplification, and I have a minus 125 dBm noise floor there. So I will just mention that, I've spent a lot of time working with my local electric utility, and I'm fortunate enough to have an electric utility that'll work with me to try to get rid of line noise. and I've been very successful with that. What's out of my control and will be out of your control are noise sources from consumer devices from neighbors' houses. You can control what's in your house, but it's very difficult to control what's coming from a neighboring house. And in my paper, I talk about a particularly egregious situation that I dealt with for a few years to the east from a neighbor's house. So, the forward peak signal amplitude that I'm recording for this is very simple. The peak signal in the direct path to the originating station. Now, that could vary a little bit. There were a few times where the peak signal was not from the direct path. It was from a skewed path or along the gray line. So whatever path provided the best signal, that's what we used. And of course, we're recording the signal level in dBm, reference to the noise floor. So with my minus 120 dBm noise floor, if I had a signal, or if I had like a minus 120 dBm signal and the noise floor was minus 125 dBm, that signal was recorded as 5 dB above the noise floor. This is just a quick list of some of the stations that I recorded data from. They were all over the world, from ASH 3V8SF in Tunisia all the way to EDI XV1X in Vietnam. And there was just, like I say, almost 100 stations that I recorded data from. So let's take a look at some of the results that I had. The forward peak results revealed that the high Z-8 array, and remember that's our array that is a high impedance system, uses all 8 antennas, verticals, all right? It provided a 1 to 2 dB increase over the Broadside End-Fire Array on some signals, because there were other times I could be looking at a signal and recording data and it would be just the opposite. Or if I was sitting there looking at some signals over time, that could change. If it started out being stronger on the high Z-8, after a while, the signal may be stronger on the Broadside End-Fire Array. The forward peak signals received from the YCCC9 were consistently 2 to 3 dB lower than any of the 8 vertical arrays. And just by comparison, again, we're using that 580-foot beverage as our benchmark beverage that we can kind of use for the comparison. So on the 580-foot beverage antennas, those signals were consistently about 3 dB lower than the BSEF or the high Z-8 vertical array. And it was equivalent to sometimes just a little bit lower than the YCCC9. Now, one interesting point that I did record as well, and I don't know why, I don't have any explanation for this, but there were times when a signal would fade down into the noise, but it would come back up out of the noise sooner on the vertical arrays than it would on the beverage. And it really had nothing to do specifically with signal, with the signal level, because sometimes the signal level would come back out of the noise at a high enough level it should have been there on the beverages. So I charted out a simple line graph here just to show some of the comparisons of the signals. Now, the top 2 signals up at the top, the high peaks, are from the 2 8 vertical arrays. And you can see that they were close to each other over the entire test. There were times when they would move back and forth. And then the lower 2 lines, the YCCC9 and the beverages. So very equivalent here of those. All right, so let's talk about some front to back and front to side comparisons. Again, the high Z-8 had a solid 25 to 30 dB front to back repeatedly when we were comparing multiple signals. The BSEF array had a front to back on the signals that we measured 20 to 25 dB. Now, the YCCC has a very impressive front to back of 25 to 30 dB that's equivalent and right in line with the high Z. But we expected that because, right, there's 3 elements. It's a end-fire array with 3 elements. So you would expect a much larger front to back than you would on the Broadside End-Fire Array. But again, you didn't have much front-to-side rejection because you have a broader forward pattern. The 580-foot beverages that I was using, I could get around 20 dB front to back and a front to side that was sort of equivalent with the YCCC 9. So once I had all of this data that I had collected off the air, I started trying to compare that to modeling data. And again, if you've read anything about receive antennas, you've heard the phrase RDF, receive directivity factor, all right? And that's really become the standard for evaluating low band antennas. And it basically takes the forward gain at any one desired location and takeoff angle, and it compares it to the average gain over the rest of the hemisphere around the antenna. Some of the early work to develop this was done by Bill Hoinstein, K0HA. And in the paper that I have, there's a lot of links that you can go back to the top band reflector and look at some of the early work that he did. So when you start looking at RDF, you know, most noise sources are going to have a direct azimuth location, but they can also be present over a wide range of surrounding areas. And you're not going to get maximum rejection off the side or the back unless it's right in the null. So that's when looking at RDF really becomes very important. So you also need to consider when you're looking at front to back and front to side data, you know, the arrival angle of the desired signal, of any undesired signals, the characteristics of noise that you have, and then, you know, any inefficiency in the construction of your array is going to come into play as well. So we took all of this data and applied it to three-dimensional plots from 4 NEC. So these are the 4 plots here. If you look in the upper left, this is the plot for the 580-foot beverages. Actually, this is for a 600-foot beverage, and it's right in line. Front to back showed it to be about 20 dB and have a 3 dB forward bandwidth of about 75 degrees. And that's right in line with what we confirmed with the online data. Now, I have RDF numbers here, and the RDF numbers that you see are what the modeling and simulation data presented. And I have a note here that I confirmed these, and how I confirmed them was actually based on comparative signal analysis over the 8 directions, all right? There's no way you're going to be able to very, very accurately do that. However, you can take the data you have recorded, and you can look at that and say, yes, my data matches what the modeling and simulation data should show. So if you go over to the upper right, this is the YCCC 9. And you can see that it doesn't really have those large lobes like the beverage shows. And front to back of about 20 dB from the modeling data. We actually saw better than that with the on-air tests. And then a 3 dB beam width of 75 degrees and an RDF of 12.1. So before I get to the BSEF, because that takes a little bit of explaining, I want to go down to the lower right where we have the high Z-8. And you can look at all 4 of these patterns, and it's quite obvious that the high Z-8 has the smallest, cleanest pattern of any of these. And the modeling data suggests a 30 dB front to back ratio, 3 dB beam width of about 50 degrees, and an RDF of almost 13.5 dB. And that is clearly what we show with the empirical data that we collected. It's a very, very nice array. So let's look at the lower left. When I saw this 3D model, I was like, what the hell's going on here? This looks really bad, all right? And it really didn't seem to jive with what we were seeing from the on-the-air data. So this really threw me for a loop, and I had to do a lot of really researching to try to understand it. And I came up with an explanation, okay? And what I concluded was, if you look at the easy neck elevation plot just to the right, you have a very high lobe that's up there at about, 60 degrees maybe. And then it sort of rolls off, and then you have another one closer to the lower part of the ground. I believe when you're doing the 3D modeling of this, that it shows the result of that higher lobe at about 60 degrees protruding off the back. And that's why you get sort of a distorted, if you will, pattern off the back. But even so, with that, and even though it shows a front to back of 21 dB, we saw on most of the signals better than that. But again, that's going to depend on where that signal is arriving off the back of the antenna. 3 dB beam width is very good, about 50 degrees. And the RDF that we could confirm by comparative results was about 12.5 dB. So, when I was doing all of this work, I had some people ask me, well, what about DX contest performance? How does it work? Well, I did not collect data during a contest, and there's a very, very important reason. My focus during a contest is to make cues and get multipliers and not sit there and document signal strength. But I can tell you that each one of these arrays has outstanding performance in contest. Now, Frank has, as I mentioned, Frank has one of these broadside end-fire arrays, and they work very, very well. But there's one thing you need to pay particular attention to when you're using an array like this in a contest. If you have areas such as Europe and South America and a big part of the United States that happen to fall in darkness at the same time, you're not going to hear weak signals, or sometimes maybe a moderately strong signal off the back of that antenna. Right, Frank? Frank's shaking his head, and we talked about this, and you're going to miss them. So you kind of need to be aware of that when you're in a contest, all right? Frequency stolen, that's right. All of a sudden you turn, look a different direction, and there's some guy calling CQ, right? Well, I go, what the hell? All right, so let's talk about our summary here, right? Phased receiving arrays, phased receiving arrays of short verticals do provide superior performance over low noise receiving and other low noise receiving antennas for 160 meters, including beverages and loops, all right? But you need to understand, the receiving antenna that's going to be right for your location is going to depend on a lot of factors. How much room you have, obviously, all right? And what's surrounding and what you can do. So you have to take that under consideration. But the empirical results from the high Z8160 that's in a 200-foot diameter, all right, consistently was the top performing antenna that I've recorded data from, all right? It produces the best overall pattern that's sharp and clean. And if I'm just using one receive antenna, that's the antenna that I use. Now, the broadside end-fire array, and again, it's in a 350-foot diameter circle, so it takes up a large area. It's a very, very close second to the high Z-8. The forward signal levels are really comparable, but you suffer a little bit in front to back and front to side, okay? But regardless of that, this is an extremely top performing antenna. Now, the YCCC9 in a 120-foot diameter circle, really, this provides some really amazing results. Even though we could really get some very deep nulls compared, that was in line and similar with the high Z-8, the forward signal levels aren't quite as strong, but if you look at the space that's required for this antenna, it's just an amazing type antenna. And here's another thing about it. If you construct it with the correct delay lines that are identified in the design and construction, you can also use this on 80 meters and 40 meters with outstanding performance. And you only need 120 feet in one line. So if you have only one direction that you want to focus in and you don't have a lot of room, let's say toward Europe, and you have 120 feet, this antenna will perform the same as a 580-foot long beverage and only take up 20% of the required space. And this is a phenomenal performer on 80 meters. It really is. Excellent on 160, phenomenal on 80. All right, so just some final thoughts here. The array that's best suited for your location, you're going to have to assess that and, the area that's required, what challenges you have. But on 160 meters, and again, I'm pretty fortunate to have a lot of room. If I'm trying to work a DX station and it's marginal conditions, I use the high Z-8 and the Broadside End-Fire Array in diversity receive. And I have to tell you, that is an absolute amazing result. So the tests here that I performed, they're simple tests, but they're accurate, okay? And I know we've had a lot of technological advances since I started recording this data in software and hardware components in recent years. And there's a lot of new things that you could use to record signal levels and so forth. And a lot of those are being evaluated right now by industry professionals and radio amateurs. So what I'm hoping is that going forward, that we can build on this work. And, I also hope that maybe it will inspire some of you folks to get out here and try to do some evaluations as well. And again, please download the paper. It goes into a lot more detail, and it has more information in there that I could really put into a presentation here. So if you haven't done that, I would encourage you to do it. And that's all I have, Tim. Thank you very much.